Welcome to Who's in STEM. I'm Ken Ono, your host, and the STEM advisor to the Provost and the Marvin Rosenblum Professor of Mathematics at UVA. This is the first episode of our third season, the 34th episode, and this is an episode that I'm really excited about because it reminds me of my youth. Our goal is to evoke flights of imagination and wonder by showcasing the cornucopia of all that is STEM at UVA, the marvelous world of UVA science, technology, engineering, and mathematics. We're going to begin this episode with a special tribute to one of my first scientific heroes, Carl Sagan, master astronomer, planetary scientist, and science communicator extraordinaire.
We inhabit a universe of galaxies. There are unstructured blobs, the irregular galaxies, globular or elliptical galaxies, and the graceful blue arms of spiral galaxies. We've been investigating the galaxies, their origins, evolution, and motions for less than a century. These studies extend our understanding to the farthest reaches of the universe. Our ship of the imagination carries us to that ultimate frontier. We view the cosmos on the grandest of scales. The majesty of the galaxies is revealed by science.
Sagan was one of my heroes. I loved his books and was a huge fan of his TV show called Cosmos. Because of his show, I wanted to grow up to become an astronaut. I wanted to be like Neil Armstrong. And as a kid, my parents bought me a telescope from Toys R Us, and I spent many summer nights in the 70s gazing at the moon and the nearby planets. Now, make no mistake, telescope sounds like fancy instrument, but my telescope was little more than a white cardboard tube on a tripod, fashioned with an eyepiece and two mirrors. Scientists, you see, have figured out that when light enters the tube and is reflected off the curved mirror and then onto a second mirror, which then bounces the light into the eyepiece, you could actually see the moon. You could see the craters of the moon. You could see the planets like Mars from your own very backyard. Now, honestly, it barely worked, but it worked well enough to inspire a kid like me. As I said, I spent summer nights peering at the nearby planets and the craters of the moon. Now, fast forward to today, and it's now 2025. Make no mistake, astronomy today isn't the stuff of cardboard reflector telescopes. And on a recent episode of Who's in STEM, we talked about the work of UVA professor Brad Johnson and his work with the Simons Observatory in Chile. You see, there are many, many kinds of telescopes now, right? You've probably heard the names Webb, Hubble, and now this very special telescope that Brad is helping to construct in Chile. In his work, he's actually using his telescope to look back in time. We talked about that, so I invite you to go back and listen to that episode to learn more about it. But just in a sentence, he's trying to understand the origin of the universe by studying what's called the cosmic microwave background. It's a great story. But there is so much to astrophysics and astronomy here at the University of Virginia, and actually in Charlottesville. We'll get into that in a moment. And I want to talk today about how the advances in computing and artificial intelligence is having an extraordinary impact on astronomy and astrophysics. You see, thanks to technology, scientists have amassed extraordinary, complex, and massive data sets about the universe. It's so massive that we need new science just to study it, to process and analyze the data. And where to turn? Well, scientists have started to leverage AI. Physicists, astronomers, data scientists, and statisticians are coming together to do a new kind of science. We've actually already seen this before. Last fall, 2 Nobel Prizes were awarded based on science that made use of artificial intelligence. A first. This trend is continuing across all of the sciences, and today we're talking about astronomy and astrophysics. I'm talking about a new consortium called the NSF Simons AI Institute for Cosmic Origins, or Cosmic AI. And it's a pleasure to welcome one member of the team, UVA's own Paul Torrey, a new assistant professor of astronomy and astrophysics. And Paul, Pleasure to have you here on Who's in STEM.
Thanks, Ken. Pleasure to be here.
So we've been talking about AI for quite some time now. And I think for most listeners, when we talk about AI, what pops to mind is probably Siri or ChatGPT, or perhaps the new School of Data Science here at the University of Virginia. Today, I want to talk about astronomy. I want to talk about astrophysics. I want to talk about cosmic AI. So, Paul, tell us about it.
Yeah, thanks, Ken. To start off, we're super excited about it. This new AI Institute, Cosmic AI, is funded by the National Science Foundation and the Simons Foundation. That's actually the same Simons as the Simons Observatory, Jim Simons. He's done fantastic things, and his foundation continues to do great work. And so Cosmic AI is an institute which is set up to try to bring AI into astronomy. Really, that's the foundational goal. Is what we want to do is build an ecosystem where we can not only leverage AI for astronomy, but then also use the use cases in astronomy to drive foundational changes or foundational advances in AI. And as you're saying, it's a remarkable time that we live in. Right now, we're seeing huge advances happen in AI. We see it happen basically every day. But even with these advances, there's still an open question, which is to what extent will those techniques or approaches that are being developed actually be brought to bear to help us advance science. And that's where this investment comes in. That's where Cosmic AI comes in. We're a collaboration between a large number of scientists spread across many different institutions. And so, of course, that's including UVA here. It also includes UT Austin, University of Utah, UCLA. But then we also have a series of federally funded facilities. So specifically NRAO, which is the National Radio Astronomical Observatory. That's actually headquartered here in Charlottesville, right on grounds.
Right. So for listeners who often drive to Crozet on the way, not far from Boar's Head, is this super important institute.
That's exactly right. Yeah, this is a site where a significant fraction of the U.S.'s radio telescope resources are managed. And in fact, there's even another site which is even kind of embedded right within campus, just a minute or two walk, 5-minute walk from the astronomy department. We also have the NOR lab, which is the optical and infrared counterpart of NRAO and SLAC. And amongst these institutions, there's a huge number of scientists that are spread between different fields. So, of course, we've got a core of astronomers, but then we also have data scientists, computer scientists, statisticians, mathematicians, and so on and so forth. Basically, it's a team that's assembled with the goal of being able to think about problems and how we can bring AI to bear on them while also driving forward the state of the field. But cosmic AI efforts are much broader than that. Two other areas that are heavily represented here on grounds at UVA are surrogate model and explainable AI inference.
So, Paul, for most users of large language models, ChatGPT, the experience is that the large language model is an amazing resource, right? It's something like being able to access the accumulation of human knowledge instantaneously. But if I understand what you're saying correctly, you're definitely going beyond that. And this is an issue that is very much in the air. We talk about AGI, right? Generative intelligence. Is what you're describing something more along those lines? So instead of just being a co-pilot that helps you do literature searches, you're able to begin to simulate the phenomena that you want to study in the universe. Would that be accurate?
So for right now, the large language models are restricted to the domain of really helping us to parse information. In fact, the way that I generally think about them is that where large language models really excel is that they're excellent at organizing information. They help us parse through disparate, different forms of information that can be collected in different places and allow us to query it in a much more natural way. Now, we do also have tools that can help us with carrying out simulations. And in fact, that's where some of these surrogate models actually come in. But at this stage, we're not yet integrating them into the LLMs. So for the surrogate models, those do have the ability to enhance our simulations. These surrogate models, classically, if I want to run a simulation, let's say I'm thinking about gravity. That's important for a lot of astrophysical topics. If I want to run a simulation, what do? Well, I write down a model where I can update in time the positions and velocities and accelerations of a bunch of mass. So if I care about gravity, my positions get updated by my velocities by my accelerations. And those accelerations are fundamentally set by the physics that's driving the system. So in this case, gravity. But that involves the solution for a bunch of differential equations. And we can do this. It's no problem. We've been doing it for decades. Surrogate models, in some sense, offer us a new option. What they do is they will observe a training set. As we're training them, they will observe a training set and provide a model that will update the state of the system without necessarily knowing the physical driver that's moving it forward. And so it actually gives us a way to approximate the behavior of gravity without directly solving the differential equations that govern it. Now, you might ask the question, why would you do this? The main advantage is that those surrogate models, in principle, can be factors of many faster than the classical approach. And so this, if harnessed correctly, could actually lead to massive increases in the scale and scope of simulations we try to run. And for someone like myself, who thinks about simulations of the whole universe, an increase in the size, an increase in the resolution we can achieve is actually critical towards really pushing forward the state of our field.
So this reminds me, so as a mathematician, I like to tell the story that Newton's laws of gravity famously assisted astronomers to locate Neptune, locate Pluto, the mathematics, the equations, together with actual astronomical observations worked together. And this is, of course, the mathematics of gravity. But on the other hand, there's this famous story of the planet Vulcan, right, that astronomers and mathematicians believed existed well over maybe 150 years ago. Because if you apply the same mathematical equations of Newton to the easier and more accessible observations of the planets that revolve around the sun in proximity to the sun, people believed there'd be a little planet called Vulcan that was very, very close to the sun, orbiting even inside the orbit of Mercury. And, of course, there is no such planet unless you are a Star Trek fan. And as Einstein famously explained, understanding gravity is like one of the hardest problems in science. And this is what gave birth to the theory of relativity. The massive size of the sun exerts relativistic effects that you have to take into account. So as a mathematician, I have to ask, is one of the moonshot problems to use your simulations to seek further evidence or tests for Einstein's theory?
So there's a lot of moonshot type ideas we have within cosmic AI. And what I'll say is that in order to get that sort of insight, you actually hit upon the next idea, which is explainable inference. In fact, these surrogate models, if we think about applying them, they function somewhat as black boxes. But if we actually want to derive physical insight, the sort of thing that would have happened when one probed what might be going on with a Vulcan-like planet, that's where explainable inference can come in. And so explainable inference is basically now asking the question, if we train our models to very accurately emulate some sort of physical system, it could actually include things like Mercury going around the sun, though admittedly that's not necessarily where our team's expertise falls. Then what you can do is you can use techniques like symbolic regression to try to actually back out the sort of physical mechanisms that are at play and are driving the system forward. And this gives us the real potential for discoveries.
So, Paul, this is a bold and exciting project. I'm glad that you are here at UVA and that UVA is participating in all of this. I think it's pretty clear that this project is not only worthwhile, it could really be transformational to astrophysics. And I don't even really know where to start. I have so many questions. But maybe let's start with the most basic of questions. In a funny way, I mentioned Star Trek a moment ago, and what pops to mind is another film. Maybe most of the listeners will recognize it. It was a film that starred Keanu Reeves dressed in black, wearing sunglasses. I'm talking about the character Neo in the Matrix. That was a film that was based on a simulation. How far off from that sci-fi Keanu Reeves Neo world are we in your work in cosmic AI?
You know, it's an amusing thought. But at the same time, it's also not the worst place to start. You know, we're not building the Matrix, but what we are doing quite deliberately is trying to build simulations that model large swaths of the universe. We're going to evolve them in time. We're going to take these swaths of the universe. We take the initial conditions from very early times, building on the sort of work that Brad Johnson does, looking at those early universe initial conditions. In the very early times, the universe was very smooth, nearly homogeneous, but there were slight density fluctuations. And through time, gravity allows those to amplify. What we want to do, what my group does, is we want to build simulations where we can put in what we think is all of the requisite physics that will help us to produce a realistic galaxy population that would match the sort of things that we actually see in the night sky. And we want to allow those models to evolve from soon after the Big Bang to the present day in order to actually test our understanding and our models of how galaxies form. So that includes, of course, gravity. I already mentioned that. But it also includes hydrodynamics, the sort of stuff that stops Earth's atmosphere from just collapsing down to be a single atom thick, right? Hydrodynamics are important for getting gas into galaxies. We also have to include a whole host of other physics. That's things like radiative gas cooling, the formation of stars. When, where, and how do stars actually form? What happens when they evolve? When they move off the main sequence and you might have a supernova explosion, how does that impact the gas in the galaxies? And then we've got these beasts at the center of galaxies, supermassive black holes. When they form, and especially when they accrete material, that can inject a huge amount of energy into galaxies. We have to include all of that. And so my group's focus is really trying to build those models with as much realism and completeness as we can. And this is important because in astrophysics, unlike, say, biology or chemistry, we can't go to a laboratory and build a star or build a galaxy. We can't do that. And so if we have questions about how various mechanisms might actually impact our model, how our assumptions about gravity might actually impact our model, we have to have numerical simulations that can actually allow us to test that.
Paul, this is really amazing. Your work, at least in the lab, sounds a whole lot like and is analogous to the very famous experiments that were described in this book by Oparin many years ago called The Origin of Life, where the idea was to come up with the axioms, the first constituents in the early primordial soup on planet Earth, right? What gave rise to the origin of life? What chemicals do you put in this flask before you start, sending electrical current through it? And they discovered that you could make amino acids with just the right ingredients.
Pretty easily.
And so what you're describing is something like this. It's the thought experiment that is getting to the bottom of what are the main ingredients, right? What are the axioms that gave birth, but realistically, practically, to the universe? So I like to draw that parallel. The origin of life and the origin of the universe are two very similar questions, but we live at a time where you can actually do the thought experiment for the universe. Yeah, that's exciting.
Absolutely. And I mean, to build on that even one step more, this is the way that we actually have evidence for something like dark matter.
So for the listeners, what is dark matter? Dark matter is not something you don't want to talk about.
No. Happy to talk about it. Yeah, our current model of the universe includes three key components. We've got ordinary matter. That's the stuff that you and I are made of, the sun, the earth, everything we see, all the stars, all the galaxies in the universe. That's ordinary matter. That is a small fraction of the composition of the universe. In our current model of the universe, we have a much larger fraction of dark matter, which is a substance that interacts gravitationally, but in no significant other way with ordinary matter. And so that's what I mean. If we talk about how do we know that exists, we see its influence on galaxies. We see how it actually shapes the evolution of our universe and the need for it to get the cosmic web we observe. But we don't, or we're not able to probe it directly using telescopes or even at this point, using laboratory experiments or high-energy colliders.
So, Paul, you said that a small fraction of the universe is actually visible to us, tangible. The dark matter is the majority. What percentage of the universe is made up of dark matter? What do we theorize?
You're in the ballpark of 20%. 4% of the universe is observable. So a diminishingly small fraction, an almost embarrassingly small fraction, right? 4% of the universe, we think, is observable. Something like 20% or so goes into the unobservable dark matter. Mm-hmm. And then the last 3/4 is an even more mysterious dark energy. And that forms the three components of our cosmological model. We can only see the tip of the iceberg, But if we want to produce a model of our universe as we see it, if we want to allow it to evolve as we see it evolving and have the properties that it's observed to have, we need these other components or our model will be inadequate.
So this is quite analogous to people who think very deeply about large language models. You wonder about the future of science. What will be the role of mankind in the future of science when large language models are ubiquitous? I think it will always be true that professional scientists, experts, will be required to fine-tune the large language models by getting the initial input data right, the initial axioms. Because in your case, if we were to run your simulations without the understanding of the existence of dark energy and dark matter, your simulations would not be compatible with the actual observations of the world we live in. So let me ask, for example, if we were to run your simulations, say, without the knowledge of dark energy, would your simulation arrive at a conclusion that's just absurd?
Yeah, absolutely. Dark energy, that really focuses on the expansion of the universe. But if I go back for a second and think about dark matter, there's so many really basic factors of the model prediction that are impacted by its presence. The classic signpost is that the rotation curves of galaxies don't match what you'd actually expect in a model that lacks dark matter. So what I mean by this is that we can step through a galaxy and look at how much mass we observe. We can count up all the stars, add up all the gas mass. Once we know that, we can use a basic gravity calculation to figure out how fast it should be rotating. But it turns out that if we do that on real galaxies, we find there is a mismatch. Galaxies are rotating faster than you would anticipate that they should be rotating if you include ordinary matter alone, if you ignore dark matter. This is, in fact, the origin of dark matter. It actually wasn't intended to be an exotic title, just rather some matter which appeared to be present that could not be seen. Dark matter is what it was dubbed at the time, and it's what stuck around. That dark matter is clearly having an influence on the scale of galaxies. But we now know there's many other potential tensions that would arise if you fail to include dark matter. Another classic example is what we call the bullet cluster. There's actually two clusters of galaxies that have collided with one another. They've moved towards each other and, in fact, have passed through each other. And by looking at that system, we can trace out where the observable matter is and where most of the mass is. And we find those two are offset. They're offset in a way that would really only be the case if you actually have some sort of dark matter there. And so if you think about how this is all impacted in terms of needing a scientist in the loop, yeah, we need someone who's actually being creative about what those tensions look like, about what sort of physical mechanisms we can implement to potentially address them. And that's exactly where the Cosmic AI team comes in and where I anticipate scientists will continue to come in as we drive forward science.
So, Paul, this is really great. Cosmic AI, I imagine when you run it and you do your work, the output is presented to you, I presume, in the form of graphs, data sets, so on and so forth. But circling back to how we started our conversation, my little tribute to Carl Sagan, I have to wonder, can you visualize as videos? Can you offer a simulation on screen, in film, in the spirit of science communication?
Absolutely. And in fact, that's one of the best parts of the job. A podcast might be the most challenging environment where I could try to describe this for you because our simulations naturally lend themselves to visualizations and we can easily render them. Just to maybe think back to a previous time we did this with a simulation known as Illustris. Illustris was a flagship simulation that we spent a lot of time making material that could be communicated to the public. What we did is we effectively put a camera inside of the simulation, and we allowed it to see various fields, ordinary matter, dark matter, magnetic field strength, whatever it might be. And we allowed those cameras to move, to actually see galaxies as they form and evolve. What this does is allows you to basically transport yourself inside of the cosmic web and see it evolve for billions of years, but just in a minute or two. You can actually get direct intuition for how these galaxies are assembling. That's useful for scientists, but it's also crucially useful for communicating to the public. The impact from Illustris and its successor, Illustris TNG, was huge, right? These are actually hugely important simulations. But if you look at the impact from the visualizations themselves, they've gotten very far out into the field as well. Those visualizations have showed up on book covers. They've shown up in planetariums. They've certainly shown up in scientific talks as well. And the reason why is because even if you don't have an expert understanding, you can quickly appreciate the complexity of galaxy formation and get an understanding about how our universe is assembling on the largest scales in just a minute or two by watching those things come to life.
Sitting here with my hat on as the STEM advisor to the provost, I can imagine courses taught using your product, virtual reality, so on and so forth. This is hard work, right? So in your role, as a communicator, as a researcher, all the hats that you have to wear to perform and produce these videos, for example, what's involved? How hard is it? What do you have to do?
Well, it starts by developing the actual simulation itself, right? Once we have that on disk, then we can make a lot of choices about how we actually want to visualize it, how we want to see it. We make choices about what we actually want to represent to the person who's looking through. Are they seeing stars or gas or dark matter? And we also make choices, especially if we're talking about science communication, about what we're hoping to communicate, what we're hoping to teach. So there's great ways that we can use these sorts of animations to actually teach a physical concept. Perhaps it's gravity. Perhaps it's about the evolution of the cosmos, the nature of dark matter. And to be quite honest, part of what goes into it also is understanding the extent to which we're trying to teach a lesson and the extent to which we're trying to just inspire folks. These sorts of visualizations can be great tools for simply getting someone interested. And so for an animation that we're going to make for a VR interactive portal that we want to create, if we're trying to get folks interested, then we're just looking to have fun. And so we're looking to animate something and visualize something in a way that's immediately going to capture someone's attention.
So, Paul, how do you build Illustris?
Yeah, so Illustris was a huge, really huge flagship simulation effort. And in fact, the history behind it is, I think, at least a little bit interesting. Really, it started with the development of a new simulation code, a repo. A repo was unique and new in the sort of hydro solver that it employed, the way it solved the hydro equations of motion. It was this new tool built by Volker Springel, one of my senior mentors. And it used something that we call a moving mesh, right? What this does is it takes advantage of all of the strengths of grid-based hydro solvers, but it allows the mesh to move and distort itself and configure itself along with the fluid flow. Now, this is really important for a cosmological simulation, for a simulation of the universe, because you start with a nearly smooth distribution of mass, but mass flows into galaxies. As it does that, the moving mesh will enhance the resolution, will put those resolution elements deep into the galaxies and allow us to really refine them well while maintaining the accuracy of using a grid-based hydrosolver. So I was really lucky early on in grad school to get involved with some initial tests of cosmological simulations using a repo. And once we had those initial tests showing that, in fact, this hydrosolver made a nice positive impact on the results that we got, then we set out to put in a comprehensive galaxy formation model. That's where we really tried to work out how we could put in a model that would reproduce the galaxies as we see them in the night sky, at least roughly. And that work, which at this point was done almost a little over a decade ago, that formed the physics engine that ultimately underpinned Illustris, and with some modifications, its successor, Illustris TNG. Now, Illustris itself, the simulation, was a huge flagship simulation effort. It was tens of millions of CPU hours, ran for 6 months on supercomputing facilities, and it's characterized with really two key major advances. The first is that it was a large volume. What that means is that we had a large population of galaxies we could study that came from a large range of environments with a large range of formation histories. And the second was that we used ambitiously high mass resolution. What that meant is that we could not just have a lot of galaxies, but also resolve them pretty well. And that combination, that's what was huge. We've made the data from Illustris public, which has had a huge scientific impact. At this point, the data from Illustris and TNG has been used in something like 1,000 peer-reviewed papers, which is really a huge impact. And it's not necessarily because it's the absolute best model that's out there. It's a really good model, but it's because the model itself can generate interesting new physical insight, and because we made it easy for people to access it. And so Illustris really kind of came about in that entire sequence. First with the development of the code, initial applications of cosmological simulations, and ultimately through building of that galaxy formation model that can then be deployed on a large simulation at scale.
So I have to ask, as you did all of this work, you provide this tool to the community, you as a researcher, how have you been able to use your own work to update our understanding of the universe?
Really in so many ways. We've done a ton of work with Illustris. In fact, it's quite varied, the things that we've actually done. If I kind of take a step back and think about the biggest things we've learned, it's probably about the nature of cosmology itself, about the nature of our universe itself. Perhaps the biggest thing we've learned is that the lambda cold dark matter, our favored model of the universe, the lambda cold dark matter model, continues to work pretty darn well. Lambda CDM basically has these principal components that we talked about previously, the ordinary matter, and dark energy. And while we might have some uncertainty about what those components actually are, we're able to integrate them into Illustris relatively straightforwardly. And if you take dark matter as an example, cold dark matter, which is our currently favored model, allows us to generally reproduce the clustering of galaxies and the structure of galaxies as we see them. Now, you asked me what we learned, right? And that's where I think a really key point comes in. We've learned that cold dark matter does really well on large scales, but that as you push to smaller scales, there are so-called small-scale tensions, right? This is basically below the scale of the Milky Way. In much lower mass galaxies, we find that the abundances and the structure of those galaxies may actually have tension, in fact, likely have tension with observation.
Well, there's a transition phase where you need a different theory, right? Same with gravity in general. Can you describe in friendly terms what you mean by cold dark matter?
Yeah, cold dark matter is really, it's a paradigm, not a model.
Yeah.
What do I mean by that? So it basically has two key components. The first is that dark matter does not strongly interact with other matter except through gravity. Okay, that's in contrast to ordinary matter. As I sit here in a chair, I'm running into the chair, right? There's electromagnetic forces that stop me from falling through this chair. But cold dark matter is different than that, right? Cold dark matter interacts gravitationally, but does not interact in other strong ways. And so what that means is we could have cold dark matter in this room with us right now. We likely do have cold dark matter in this room with us right now, passing through us, passing through the Earth. It does that, no problem. Now, the cold part implies something about how it moved. Well, it could be the mass of the particle, but really how it moved in the early universe. Hot dark matter would be something that's a relativistic species. Streams very fast, would make it hard for structures to collapse on small scales. Cold dark matter is the opposite. It's a big particle, moves slowly, and allows for an abundance of structure even at very small scales. That's the model that's currently our favored one, but it's not one without tension with observations. This is kind of the question. What's the composition of dark matter? Now, hot dark matter is ruled out as being a large portion of the dark matter model, but it could still be some fraction of it.
Now, for listeners, I'd like to talk a little bit more about the dark matter because I think this is important, and not because of the physics, but because one of the most important figures in this story was a leading woman in science who happened to be the mother of one of my colleagues, a very famous number theorist named Carl Rubin, who works in my field. By the way, all the Rubin kids ended up becoming famous scientists. Vera Rubin, I got to know before she passed away, was a dominant figure. She discovered dark matter, and she went on to be a leading figure for women in science. She was a strong supporter for women in science, and I want to celebrate her today, just like we opened with Carl Sagan. Can you tell us about Vera and how important she is to all of your work?
Yeah, what a tremendous figure in our field. So Vera Rubin really was responsible for seeing dark matter when no one else did. What she did was try to understand the influence of gravity on the structure of galaxies and to map out in as much detail as they could how galaxies were rotating and compare that against the mass they could actually find. At the time that she was doing this work, she anticipated that she would be able to actually account for, get a total census of the material in these galaxies. But she found there is a discrepancy, right? And think about what you might do in that moment, right? An almost embarrassing discrepancy. She couldn't find a significant fraction of the material, right? But she wasn't wrong. She, in fact, was exactly right. She had the bravery to kind of confront that and say, there's something else going on here. There's something missing. There is another type of matter in these galaxies. There is a dark matter here, right? And that was a seminal contribution. She was able to actually identify the fact that there is something else that no one else could see. She was the first one to really identify it. Really, she changed the landscape of our understanding of the universe.
Thank you, Paul. I know that's a little bit out of the ordinary for our conversations that we have on Who's in STEM, but I knew her, and I'm glad that you raised this. I think she should have won the Nobel Prize, and I think there's a second dark matter here. Not only did she discover dark matter, but there's also the dark matter that for most of her career as a woman in science, she was discriminated against. So thank you for sharing that with me. She was an amazing woman. Paul, this has been a great conversation. While we're still on topic, because we do have to wrap up very soon here, I have to ask, what initially sparked your interest in computational astrophysics?
Yeah, well, it certainly wasn't a linear path. Trying to not go back too far, I always was interested in math and eventually physics in high school. And that drove me towards wanting to be a physics major. The problem was I didn't know what a physics major would do, right? I had no clue how this would actually lead to possible career paths. And so when I went to college, I went to undergrad at Cornell, where I was an applied physics major. And that's a crucial little bit of information because the applied physics majors sit in the engineering college at Cornell. What that meant was that all of my mentoring and all of my advising and all of my colleagues were coming from more of an engineering background. And so kind of like a chameleon, I took on that sort of environment. And my first jobs were actually engineering jobs. My first internship was at Lutron Electronics, helping to redesign some light switches. And I'm really grateful for that job. I actually learned a lot from it. But I did want to seek out something else after that maybe would be a different application of that sort of engineering principles. So my next internship was over at the Jet Propulsion Laboratory, where I was studying Hull thrusters. And we were looking at what would happen if high-energy ions came out of these electric propulsion systems and wrapped around the magnetic field lines. Ended up coming back towards the spacecraft, right? This is a bad idea. If you design a spacecraft that is going to etch away at itself, that's a very bad idea for the longevity of that spacecraft. And so during that internship, what I really learned was that I loved the numerical modeling. And I loved being curious, trying to understand the system, trying to model the system. And so from there, I took one more step, this time just kind of going over the edge into just pure science. I worked with Joe Burns at Cornell, trying to understand the dynamics in Saturn's rings, specifically the wavy edges of the Encke and Keeler gaps. There's these little moons that sit in each of those gaps. And as material passes by them, it pulls on that material. The moons pull on them. And so you can get these interesting patterns. And I really, as I was digging into that project, just had a fantastic time. And that, for me, that combination of experiences allowed me to begin to drill down and say, I love doing numerical work. I love being curious. I love trying to understand interesting systems. And ultimately, that's what led me down this path to the computational astrophysics I do today.
Well, thank you for sharing, Paul. The work that you do certainly sounds a lot more exciting than studying the dynamics of light switches, but I'm sure that was very important. So last question, an off-the-wall question. Tell us one fun fact about yourself for our listeners so that they can have an image of you beyond computational astrophysicist.
Well, yeah, as we sit here at UVA, perhaps interesting to know, I grew up here in Virginia. I grew up in Fairfax County in a place called Herndon. I love bringing this up with my classes, kind of asking them where folks are from. If it's a big enough class, there's almost certainly one person who grew up not that far away from me. Man, I grew up really admiring this university. And so I went off to college and grad school, spent some time in New England, spent 5 years at the University of Florida on the faculty there, but always had a real interest in cycling back and getting back to UVA. And Really excited to be here. Really consider myself lucky to be back at the University of Virginia. So that's a little fact that I think hopefully resonates with students, that my roots come not far from here, came out of the public school system in Virginia. And I'm really excited to now be working at this university that I always grew up admiring.
Well, you may feel lucky to be here at the University of Virginia, but we feel lucky to have you. This is great science. You're a great professor. I'm sure you're inspiring to your students. How can students get involved in your work?
Come on over to the astronomy department. Come to our journal club discussions. We have them twice a week. Come to our colloquia. We have those once a week. Come listen to what the graduate students and the postdocs and the faculty are doing. Get to know people. Embed yourself in that environment. We are a very open community. And there's a ton of opportunities for folks to learn about what's happening in the department and ultimately step into positions where they're contributing to what's happening in the department. So in the astronomy department, we have a long history of involving undergraduates in research. We have a long history of helping students really get up to the forefront of astronomy research. Those students need not be shy. Just come on over, come to the journal clubs, come to the colloquia, learn about what's happening, and use that as an opportunity to get to know some people as a launching point for getting involved.
Well, Paul, great. This has been really an inspiring and pleasurable conversation. You are fulfilling President Ryan's mission to be great and good in everything that we do. And I'm Ken Ono, STEM advisor to the provost and the Marvin Rosenblum Professor of Mathematics. And you've been listening to Who's in STEM.
Who's in STEM is a production of WTJU 91.1 FM and the Office of the Provost at the University of Virginia. Who's in STEM is produced by Catherine Kosseboom, Claire Curzon, Benjamin Larson, Mary Gardner-McGee, Katie Nichols, and Ria Verma. Our music is composed and performed by Robert Schneider and John Ferguson of Apples in Stereo. Follow us on Facebook, Instagram, and Twitter. Listen and subscribe to Who's in STEM on Apple Podcasts, Spotify, or wherever you get your podcasts. We'll be back soon with another conversation about scientific and technological innovation at the university.